Calculating solubility from KSP. The strategy for solving this type of problem is similar to that of finding the hydronium ion concentration for a weak acid solution from the initial concentration of the weak acid. In those problems, an ICE table was used to find the equilibrium concentrations of weak acid, hydronium, and conjugate base. An ICE table is also used here, where X is the solubility. Many texts use S in place of X, which is used in weak acid calculations. Example 1, calculating solubility from KSP. What is the molar solubility of a saturated aqueous solution of barium carbonate if KSP is 5.0 times 10 to the minus 9? Let's start by writing the equilibrium equation. So we can see that for every mole of barium carbonate solid, we have an equilibrium with 1 mole of barium ions and 1 mole of carbonate ions. The equation indicates a 1-to-1 ratio of barium ions and carbonate ions in the solution. The molarity of one of the ions then will be the molar solubility of the barium carbonate solid. All right, so let's start with the dissociation and what happens in our ICE chart. So we have the dissociation of barium and carbonate. We start out with none initially. We have some change, right? For every amount that dissolves, 1 mole of each or that same amount is produced. So we have some change X. So that at equilibrium, the amount of barium ion and carbonate ion are both some unknown value X. KSP, we know it's given as 5.0 times 10 to the minus 9. It's the product of those two equilibrium concentrations. So I substitute X for both of them and get X squared. Solve for X, I get 7.07 times 10 to the minus 5. Remember, what did we set X equal to? It's the barium concentration and the carbonate ion concentration. Since 1 mole of barium ion or 1 mole of carbonate ions are required for 1 mole of barium carbonate, the molar solubility of the barium carbonate is the same, 7.07 times 10 to the minus 5. Example 2, calculating solubility from KSP. What is the molar solubility of a saturated aqueous solution of PbI2? KSP equals 1.39 times 10 to the minus 8. All right, let's start with the equilibrium equation where PbI2 solid is in equilibrium with Pb2 plus ions and 2 I minus ions. The equation indicates a 1-to-2 ratio of Pb2 plus and I minus ions in the solution. So the molarity of the Pb plus ion is the molarity of the PbI2, or the molar solubility of the PbI2, and that's what we're looking for, right? Because that's the one in the lowest molar ratio. Given the stoichiometric coefficients, at equilibrium we have some amount X of Pb2 plus ions and 2X of I minus ions. We can substitute that into our KSP expression, where KSP is given as 1.39 times 10 to the minus 8. And that's the product of the lead 2 plus concentration times the I minus concentration squared. Remember, we include our coefficient as an exponent in our equilibrium constant expressions. We substitute X for the lead 2 plus ions, 2X for the iodide ions. We square that. This is 4X cubed. Solve for X, we get 1.51 times 10 to the minus 3rd. Since 1 Pb2 plus ion formed from 1 PbI2, the molar solubility of PbI2 solid is 1.51 times 10 to the minus 3 molar, the same as the lead 2 plus ions.